Thank you very much for introduction. I'm Tasek from KAIST. Today I will talk about MetaSense, few-shot adaptation to untrained conditions in the mobile sensing. And this is a joint work with my brilliant collaborator Yeonsu Kim and Professor Shin and my advisor, Professor SJ. So the era of mobile sensing. In this tiny device, there are just various sensors. Utilizing these built-in sensors and applying deep learning, various mobile sensing applications have been proposed, such as activity recognition, emotion recognition, to mobile healthcare. These mobile sensing applications have the potential of mainstream adoption, as users could enjoy these mobile sensing applications only within their devices. However, those mobile sensing applications face performance challenge when they are deployed in the wild. This is because while deep learning performs well under trained conditions, it performs poorly under untrained conditions. Specifically in mobile sensing, different users have different conditions, and we call it individual conditions. For example, users have different behaviors and physical conditions, and their devices as well have different sensor specifications and locations, and so on. And those combinations of different users' behavior, physical conditions, and their devices' sensor specifications and locations make unique individual conditions for users. And those individual conditions make sensor input different. Here's an example. For the same activity walking, the sensor readings are totally different according to individual conditions. And as there are countless users and devices and combinations between them, training a deep learning model on all the conditions is infeasible. So there have been many trials to resolve this individual condition problem. The first category is sensor calibration. For example, summing the square root of XYZ axis of accelerometer values to make a sensor orientation independent feature. However, these approaches target a particular condition problem, such as sensor orientation only, and those approaches are usually tailored to a specific sensor or specific application. So this is not a general solution for mobile sensing. And the second approach is more of machine learning based solution, transfer learning with utilizing target data, unlabeled target data. While the advantage of this approach is it doesn't require manual labeling from users, it still requires hundreds of target data, so it takes time to collect them. And according to a recent work that applies this method in mobile sensing, it sometimes performs worse than without it due to the fundamental limitation of unlabeled data. So our research question arises here: is there a general solution to overcome such countless individual conditions with only few data? So we present MetaSense, few-shot adaptation to untrained conditions in dim mobile sensing. MetaSense is model and condition agnostic. That means its coverage is not limited to a specific model or specific condition. So it's a general approach. And second, it requires only few data, just one or two, to adapt to the target condition. And third, MetaSense shows high accuracy and outperforms the existing state-of-the-art baselines. And finally, MetaSense requires significantly less adaptation time compared to adapt to the target condition compared to existing approaches. So MetaSense achieves these strengths by meta-learning-based few-shot adaptation to the target condition. Here, one shot means one label sample per class. Activity recognition, for example, one sample for running, one sample for walking, like that. So utilizing meta-learning, MetaSense can adapt to the target condition with only few data. Then what is meta-learning? Meta-learning is also known as learning to learn. The goal of meta-learning is to imitate the human's ability of learning new concepts quickly with a few data. Here's an analogy. if one is trained to play tennis, then one can easily learn how to play badminton or play table tennis than who isn't. Similarly, MetaSense trains a base model, which is trained on condition changes, so that if it meets a new condition that it has never trained before, it can adapt to that condition with few data, like this. But this is possible only if the base model is trained in a way that it can adapt to condition changes. So the question is how to train the base model. Our key intuition of adopting meta-learning here is by rehearsing condition changes while training the base model will be trained in a way that it can adapt to condition changes. So the objective of meta-learning here is learning to adapt to new conditions. And this is the overview of MetaSense. MetaSense is composed of two parts: base model training, and after the training of the base model, adaptation in the deployment stage. So in the base model training, we assume that the developer has collected several data sets from multiple conditions, which is common in mobile sensing, and we call it source data set. And from the source data set, we generate multiple tasks by our unique task generation strategies. And with these generated tasks, we train the base model via meta-learning. And after the training of the base model is complete, now it's ready to be used. Given few shots from the user, the base model can adapt to that condition by updating its parameters. So let's start with how task generation works. Before going into how task generation in MetaSense works, let me explain how existing meta-learning generates tasks to emphasize how MetaSense differs from existing meta-learnings. So task in general means a single episode for training the model following the meta objective. And specifically, task in traditional meta-learning is encountering new classes that the model has never seen. So task in traditional meta-learning is, here's an example. So in task 1, the model learns cats and birds with few shots and predict if the task image is cat or bird. But in task 2, the model learns flowers and bikes with few shots and predict the task image is flower or bike. So by iterating this process, the traditional meta-learning trains a model that can learn new classes quickly with few shots. And here, tasks are generated randomly sampled classes from a large data set like ImageNet. However, there are unique challenges and considerations in task generation for mobile sensing. First of all, as I mentioned before, there are countless individual conditions. So the question is how to let the base model experience as diverse individual conditions as possible. And second, as it requires tremendous effort to collect the data set for each mobile sensing, the amount of the source data set is usually limited. So the question is how to effectively and efficiently leverage the limited source data set. Finally, existing meta-learning algorithms assume learning new classes, but our task is not learning new classes, but adapting to condition changes that makes input distribution different. So in comparison, task in traditional meta-learning is encountering new classes that the model has never seen. And these tasks are generated randomly sample classes from a large data set. But task in MetaSense is encountering a situation where the base model performs in a new condition. And these tasks should be diverse and generated from limited data, and the target task has the same label set, unlike traditional meta-learning. So to meet this requirement and overcome those challenges that I mentioned before, we devised 3 task generation strategies. So let me explain how task generation in MetaSense works. So in this example, the source data set is composed of 5 individual conditions. And from the source data set, we first generate per condition tasks. Each per condition is derived from each individual condition in the source data set. And the purpose of per condition tasks is to let the base model experience multiple real individual conditions in the source data set. And second, we generate multi-condition tasks by selecting random individual conditions from the source data set and mixing them across labels. The purpose of multi-condition tasks is first, to make as diverse tasks as possible, and second, to avoid possible overfitting to the per condition tasks. And finally, unlike existing meta-learning algorithms where the tasks are generated randomly, when we generate per condition tasks and multi-condition tasks, we keep the label set. By doing so, the base model can leverage the common knowledge learned from homogeneous tasks. So we call it homogeneous task generation. And with this generated tasks, we train the base model. Each task acts as an adapting to each condition, and base model adapts to each condition by supervised learning. When the base model conducts supervised learning, there are 2 restrictions. The first one is it uses only few gradient steps in with few shots. These 2 restrictions ensures that the base model should adapt to the target condition rapidly with few shots. So after conducting each task, the base model now has adapted model parameter, from parameter theta to theta prime for each task. And with these adapted models, we evaluate these models and calculate loss. And the objective of meta-learning here is minimizing the sum of task losses and then update our parameters of our interest, theta. So by iterating this process, the base model will learn effective parameter theta that can adapt to condition changes rapidly with few shots. So after the training of the base model is complete, now it's ready to be used. Before using a mobile sensing application, given few shots from the user, the base model can adapt to the target condition because it's trained well how to do that in the base model training. So let's move on to evaluation. In this presentation, we try to answer 3 questions through evaluation. First, how well does MetaSense perform against existing approaches? And second, how effective are MetaSense task generation strategies? And third, how rapidly MetaSense can adapt to the target condition. For data collection, we recruited 10 different users and assigned them 10 different devices, and there were 7 different smartphones and 3 different smartwatches as listed in this table. And each row in this table represents an individual condition. And we conducted 2 tasks. The first one is activity recognition with 9 activities, and the second one is speech recognition with 14 keywords. The reason why we selected these 2 tasks is they use common sensors for mobile sensing, IMU and microphone. And here are the baselines. Source means training a deep learning model with the source data set only. As we collected 10 individual conditions, we used 9 conditions as the source data set and the remaining 1 condition as the target data. And the target means training a deep learning model with the target data only, which means few shots. And source plus target means training a deep learning model with both the source and the target data. And the TRC is the state-of-the-art transfer learning with few shots for human activity recognition in mobile sensing. And we also compare MetaSense to 2 popular meta-learning algorithms, PN and MEMO. PN generates prototypes for each class with few shots and classify the task input to the closest prototype generated. And Mammal trains sensitive model parameters for task changes. And this is the result. The upper figure shows the accuracy for activity recognition, and the lower figure for accuracy for speech recognition. And we have 4 cases when the user gives only 1 shot, 2 shots, 5 shots, and 10 shots. And naturally, as the number of shots increases, the accuracy goes higher. And note that as the number of shots increases, target outperforms source. This again highlights the importance of adapting to the individual conditions in the mobile sensing, because using only target data outperforms source that uses more than 9 times more data. And it's interesting to note that different data sets shows different accuracy trends. So for example, while source plus target shows low accuracy in activity recognition, in speech recognition, source plus target shows relatively high accuracy. And this is because the data distribution in speech recognition are more similar compared to activity recognition, and thus the learned representations from the source data is more transferable to the target in speech recognition. But still, MetaSense shows its effectiveness in both data sets. And you can see that MetaSense is better than the transfer learning approach. And this is because the underlying assumption of transfer learning is that the learned representation in the upper layers are transferable to the target task, but meta-learning-based solution is more powerful in a sense that it can adapt to condition changes without this assumption. And overall, MetaSense outperforms the baselines thanks to its well-generated tasks and parameter updates via meta-learning. And we also measure the effectiveness of our task generation strategies. Here, random means random task generation, which is widely used in existing meta-learning solutions, and per for our per-condition tasks, and multi for our multi-condition tasks, and homo for our homogeneous task generation. And as each of our task generation strategy is added, the accuracy goes higher. And this explains why MetaSense is better for mobile sensing than existing meta-learning schemes. And we also investigate how many training epochs are required for MetaSense to adapt to the target. And we plot accuracy graph according to the number of training epochs. So as the number of training epoch goes on, the accuracy goes higher. And as you can see, MetaSense requires significantly less adaptation time compared to the baselines. And this is because we set a restriction when we train the base model. And this is a great benefit for resource-constrained mobile sensing. So in conclusion, we present MetaSense. To the best of our knowledge, this is the first meta-learning-based solution for adapting to untrained conditions in deep mobile sensing. And we propose 3 task generation strategies to resolve the challenges in adopting meta-learning to mobile sensing. And finally, our results show that MetaSense outperforms transfer learning by 18% on average, and other meta-learning schemes by 50% on average in terms of accuracy. And that was MetaSense. We believe MetaSense is a step towards the mainstream adoption of mobile sensing for practical impact. And feel free to visit our website for more information. And thank you for paying attention, and I'm glad to take any questions.